Hey, just gonna wait another minute or so. Hi everyone. So, my name is Dante. I'm one of the problem setters for ACPC. I wrote 3 problems, so this one, Best Investing, and also 2 problems which were only for Division 2. Those were Test Drive and Warring Scoring. So, those ones are a bit easier. I'll answer questions about those at the end if you guys are interested, but I'll be focusing on this Best Investing problem. So, Um, so in this problem, we have Geraldine who's designed this portfolio that's guaranteed to grow at R% every year. So because it's R% every single year, that kind of gives you the clue that there's going to be something about compound interest and exponential growth in this problem. So we have this investment portfolio, and she wants to maximize how much she can get out of it. So she has Y years in which each year she can either deposit money into or withdraw money from her account once a year. So this once a year, basically, it's just to make this discrete problem. So you have discrete length of time for each year, and you have one action you can take each year, which is either depositing or withdrawing money. So every year that money stays in the account, it's going to grow by R%. And her account stores this amount as a real number. That's just to make sure that you guys don't have to round to the nearest cent or do something like that. So the fun part of this problem is that there's these limits. So Geraldine can only deposit up to D dollars per year if she chooses to deposit, and if she chooses to withdraw, she's not going to withdraw more than W dollars per year. So she can't just deposit a huge amount of money and withdraw all of it. She has to be somewhat clever because of these limits. So the problem statement is that if we start with an empty account, so there's 0 in it, and we go for Y years, what's the maximum net gain that she can earn? So net gain, I just mean the maximum amount of withdrawals minus deposits, so the net profit that she can get from the account. So let's look at this first sample input here. There's 4 numbers. So the first one is R, this rate at which it grows. So in this sample input, R is 5, so we have 5% growth every year. Then we have Y, so that's the number of years. And Y years, so in this case there's 1 year. So that means that there's going to be 2 actions that she can take, which are at the point 0 where we start, and then at 1, which is 1 year after we start. And in between, whatever she puts in is going to grow by 5%. This 1,000 means that she can deposit up to $1,000 in each year interval, and 2,000 means she can withdraw up to $2,000. So the best strategy here is actually pretty simple, I think, because there's just 1 year. So the only way you can make any money is if you deposit at first and then withdraw after. So might as well deposit as much as you can. So she deposits $1,000 right away. Then she waits 1 year. This 5% growth means that it'll grow to $1,050. And then at the end of this year, she withdraws the full $1,050. So then the solution is going to be the difference between her total withdrawals, 1,050, and her total deposits, 1,000. So in this case, 1,050 minus 1,000, you get 50. So this is the easy sample case, but it does give you a bit of a hint as to what the optimal solution is going to be. Because here, we only really had 2 actions to take after 0 years and after 1 year, but we deposited first and then we withdrew, and we deposited as much as we possibly could, and then we withdrew everything that was in the account, which does suggest what you should do to in a more general case. So, yeah, so because our investments only grow with time, this means that our optimal strategy is going to be to deposit as much as you possibly can and then withdraw as much as you possibly can. So we end with an empty account. So the reason that we want to end with an empty account is because if we had anything left over at the end, then that would mean that that's something that we've deposited without taking advantage of it at the end as a withdrawal. So if we hadn't deposited the amount that eventually ended up being there in the end, then we've lost out on money. So we want to start and end with an empty account, depositing as much as possible, and then withdrawing as much as possible. So there's more than one way to solve this problem, but the way that I did it is we basically have two pointers that are going through all the possible years, so going from 0 to y. And one pointer is looking at when we're depositing, the other one is looking at when we're withdrawing. And the depositing one is going to go forwards, and the withdrawing one is going to go backwards. And the key insight here relative to compound interest is that if you have any amount x that you put into the account, after y years, it's going to grow, and that's actually a mistake. This should be x times this number. So it's going to grow to x times 1 plus r over 100 to the power of y. Yeah, because this is just telling you how the exponential growth inside of the account is going to go. So we'll look at a specific example of the second case. We already looked at the first one. The second one's a little bit more interesting. So r equals 100. That means that the rate is 100%. So every year, the amount in the account is going to double. And we have 10 years. We can only deposit $1 per year, and we can withdraw up to $1,000 per year. So this is just the same thing in text. So yeah, so the money is going to double every year for 10 years, and we can withdraw. We can deposit at most $1, withdraw at most $1,000. So how is this idea with the pointers going to work? What I'm going to do is that so in this case, because y is equal to 10, we have 11 actions, basically, from year 0 to year 10. So 1, 2, 3, 4, 5, 6, 7. So now we have 11 actions corresponding to the 11 sort of points that are around these 10 years. So remember, we start by depositing as much as possible. So we're going to start looking at year 0. We want to deposit as much as we possibly can. Well, that just means depositing $1. So we want to deposit $1 into year 0. And the way that I look at this is that, okay, we deposit $1. If we kept this all the way to the end, what would $1 grow to? Well, because the rate is 100, and that means that we're doubling every year, it's going to grow to 2 to the power of 10, which is 1,024. So that means that in the after 10 years, we can withdraw not quite everything, because 1,024 is bigger than 1,000. So we can withdraw 1,000, but then we have this 24 left over. Now this is where the going backwards with the withdrawing pointer, what this means, because if we can withdraw 1,000, we haven't withdrawn everything that eventually came out of this $1. And we have these $24 left. So what do? We go back 1 year, and we're looking at, okay, after 9 years, how much can we withdraw? Well, if we have these $24 that we would have withdrawn after year 10 if we could have, because we don't, we go back 1 year and we divide by 2 because we're undoing one of these doublings, and we have 12 left over, which means that we have $12 that we can withdraw from this $1. So this 24 turns into 12 because we're going back 1 year and we can afford one less doubling of the amount. And that's everything that we can get out of this first $1 that we've deposited. So far we've deposited $1 and we've gotten $1,012 out. So now because we've deposited as much as possible, we move this depositing pointer forwards and we say, okay, the next year, well, we're going to deposit one more dollar. Now this $1, if currently we're looking at after 1 year and we're looking at after 9 years. So this $1, 8 years later, is going to grow to 2 to the power of 8, which is 256. And so we have 256 more dollars that we can withdraw after 9 years. So far this hasn't added up to 1,000, so we don't need to move this pointer when we withdraw. So we can keep going. We're going to say, okay, we're going to deposit $1 after 2 years. So 2, now from 2 to 9 is 7 years, so 2 to the power of 7 is 128. So every time we advance the depositing pointer forwards, or we bring this withdrawing pointer back, the difference between the years that we're looking at goes down according to the rate, and that's going to be part of the algorithm that does this. So now you can see that if we keep going, if we keep depositing $1 every year, we're just going to keep moving this pointer forwards. Oops. And it'll just turn out that it's never going to go, in this case, it's never going to go above 1,000 after year 9. So we keep adding these numbers until the very last one, which is year 8, when we deposited $1, and then 1 year later, it grew to $2. So we have this sum that 12 plus 256, 128, 64, etc., all the way down to 2. And it turns out that these numbers, if you were to add them up together give you 522, which you can verify on your own if you want. And so the solution to this sample case is going to be, well, the total amount that we withdrew at the end was 1,522. So this 1,000 here plus this 522 after year 9. And then we subtract these 1, 2, 3, 4, 5, 6, 7, 8, 9 withdrawals of $1 each, which gives us $1,513, which is the solution to this to the second case is $1,513. So this is kind of this is my visual idea of how this algorithm works. And also for this third sample input, if you take a look at this one has a rate of 7% per year, and 100 years, we can deposit up to $1 and we can withdraw $100,000. So it turns out that for this particular sample input, the optimal strategy is actually just going to be to deposit $1 every single year until $100 have passed, and then withdraw everything. And if you withdraw everything, you get 13,248 point this stuff, and then we subtract the $100 that we input at the beginning. So in this case, if we were to run this this idea with these pointers going forwards and backwards, we would get that the pointer with the withdrawal is going to be stuck at year 100, and the pointer with the deposit is going to move forwards. Yeah, any questions up to this point? I'm going to show you my code that actually implements this. I'm not seeing anything in the chat. Right, so I'll show you my code so that you can also see kind of here. So this code, I wrote it in Python, which is hopefully easier language to read. So first of all, I'm just going to build up the solution as a, maybe I could write a 0.0, but Python doesn't care. But it's going to be a floating point number that's going to store the profit that we have of withdrawing everything minus depositing everything according to what's going on here. So the rate, it was given as an integer, and we want to convert it into a floating point number that you can just multiply every year. So this is just saying 1 plus r over 100. That's just saying this is converting it from, so if it's r%, it'll be r divided by 100, then plus 1, just so that this is going to be the number that we multiply by for money that's inside of the account. So with the doubling example, for example, r was 100, and this is going to turn into 2. Or if r was 50, it's going to be 1.5. Withdraw year and deposit year, these are those two pointers that I talked about. So this is which year are we looking at for withdrawing, and this one is which year are we looking at for depositing. So just like we did here, we start by withdrawing at the very end and depositing at the very beginning. And as we're going to go forwards, we're going to see that the withdraw year is going to go down and the deposit year is going to go up. Deposit left, that's telling you how much do we have left in this particular deposit year that we can deposit into the account until we've reached our maximum. So we start at D because that means that when we start, we can deposit up to D dollars. If we were to deposit some portion of this D dollars, then this deposit left is going to change, which I'll get into in more detail later. And this W is same sort of idea with the withdraw left. So this is how much can we withdraw left before we have to move the withdrawing year, because we've hit the maximum of withdrawing. So then we do a loop here where we're checking if the withdraw year is greater than the deposit year. So we want to check that we're always looking at two distinct years, because eventually once this algorithm finishes, what's going to happen is that the two pointers are going to be pointing to the same location, and because we can only either withdraw or deposit in a single year, then that means that we've finished at that point. So what we're going to do in each step, we're going to try to deposit as much as we possibly can. So if you remember, in this case, we started out by depositing $1 into here, and then if we were to withdraw $1, we calculated here that the oh, now I need to get my code back. Oh no. Okay, so if we, oh my goodness, no, sorry, I knew something was going to go wrong. All right, so if we deposit $1 at first, and we calculated that after the 10 years we would have 1,024. So this is what we're doing here. We're going to see, okay, if we were to deposit everything, then how much would we be withdrawing at the withdraw year that we're currently looking at? So to calculate that, we're saying, okay, how much are we deciding to deposit? So deposit left is how much do we have left to deposit in this current year? How much are we allowed to? And then we're going to see what's going to happen if it grows exponentially for the amount of years that are in between the withdrawal year and the deposit year. So in this case, we had 10 years from the 0 to 10. So this is 10 minus 0. And the rate in this example, which was a second sample case, is 2, or 1 plus 100%. So in this case, we would see that this is 1 times 1,024. So this is saying if we did a maximum deposit, how much would we be withdrawing at the end, at that withdrawal year? So now we had to be careful, because remember, this 1,024 was actually too big. So this is what this if thing is looking at here. So it's saying if the withdrawal is smaller than withdrawal left, so if the amount we're trying to withdraw, in this case 1,024, is less than how much we have left to withdraw, which in this case is oh, sorry, no, this yeah, if the amount that we're trying to withdraw, 1,024, is less than the amount that we have left to withdraw, 1,000, then we can make that full deposit. In this case, we have 1,024 less than 1,000, which is false, so we jump to this the else clause, which I'll go through. So in this case, we're saying, okay, we can't actually make a maximum deposit because of the limit of how much we can withdraw. What we can do instead is make a maximum withdrawal. So we're going to kind of look at it in the other direction. So we're going to change how much we're going to deposit to be the amount that we're withdrawing left, and then times the exponential growth in the opposite direction. So here we had withdraw year minus deposit year. Here you have deposit year minus withdraw year, which means we're looking at this $1,000 back in time. How much would you have to deposit? So this will be 1,000 divided by 1,024 is what this whole expression is going to come out to. And so we're going to say, okay, that's how much we are able to deposit without going over our withdrawal limits. So the amount that we can deposit left, we subtract the amount that we're actually withdrawing. And then this solution that we're building up is going to be how much we're actually going to be withdrawing. And withdraw left means this is everything that we can withdraw. Withdraw all of it minus the amount that we actually ended up depositing. So we're building up the solution using these differences here. Once we've done that, we move the withdrawal year back because we made the maximum withdrawal, and then we reset the withdrawal left because now we're in the year before that, so we can withdraw all of the W. Now in this case, once we've done this for one step, we would have moved the withdrawal year from 10 to 9, and we'd still be looking at 0. And we'd have a little bit of depositing left, which is going to correspond to this 12 over here. So the next time that we go through this loop, we're going to see that this withdraw amount here, when we calculate this is going to end up being this 12 that we found over there. And this is going to come out to be true this time because this is going to be 12 and this is going to be 1,000. So we can withdraw the $12. So in this case, this code is pretty similar to this. It's just saying that the amount that we have left to withdraw for that year, we're going to subtract 12 in this case, and then we're going to add to the solution the amount that we withdrew, which is 12, minus deposit left, because in this case we are making a maximum deposit. In this case, we're going to be adding 12 minus 1. And then here, instead of pushing the withdraw year pointer backwards, we're going to push the deposit year pointer forwards and reset the amount that we have left to deposit. So we continue this loop until we get to the point where the two pointers looking at the same thing, and then we can just output the solution. Yeah, do you have any questions? Yeah, I don't see anything in the live chat. Would you guys like to look at my other two problems as well? Or those ones are kind of the easier ones. But yes? Okay. Sure. So my other problems were quite a bit easier than this one, but I can go through them quickly. So yeah, so one of my problems was called warring scoring, and these ones were the Division 2 only problems. They were kind of the somewhat easier ones, though easier, but you still kind of have to read it carefully. So in this warring scoring, the idea is that we have these two people who are playing ping pong over and over, and they're getting tired of how they're deciding who wins, and they decide on two different scoring systems. So one player, not numbed, decides that the player with the longest consecutive streak of points wins. So if one player gets like 5 points in a row, the other player only gets 3 points in a row, and the player who gets 5 points in a row will win, if this is your longest streak. And then Irreglax system is that the player who held the largest lead at any point in time wins instead. And both systems also have the the possibility of a tie. Like if the longest consecutive streak was the same in both cases, then it's a tie. Or if both players at some point held their maximum lead was equal to each other, then that would also be a tie. So sometimes the two systems agree and sometimes they don't. And the idea of this problem is just, okay, let's figure out when do they agree and when do they not agree. So there's a whole bunch of points, because I guess Irglak and not nommed have a lot of time in their hands. There can be up to 10 to the 5 points. And the way that it's input is just we have the name of the player who scores a point. So in this sample input, we can see that in not nommed system, which is the longest consecutive streak, we can see right away that not nommed would win because he has a streak of 5 as opposed to 3. In Irglak system, it's who has the biggest lead at any point in time. So after 3 points, Irglak has a lead of 3 points. And then after this, not nommed scores 5 points, but even after 5 points, not nommed's lead is only 2. So in this case, Irglak would win under Irglak's own system, and not nommed would win under not nommed's system. So they disagree with each other, and hence the disagree over here. And then I have a few other examples. So here, for example, we see that both players have a streak of 2. And then if you look at the lead, so Irglak is winning by 1 point, then it's a tie, then not nommed is winning by 1 point, then it's a tie, then Irglak is winning by 1 point. So both of them, their best lead is 1 point. So in this case, it's a tie under both systems. So hence they agree. And in this case, they both have a longest consecutive streak of 2. So they tie under not nommed system, but not nommed's lead is 2 points after the first 2 points have scored, and Irglak never has a lead. So it's a tie under one system, but a not nommed win in the other system. So this one is disagree. So this is kind of the problem where it takes a little while to explain what's going on, but I think in order to understand it and implement it, there isn't a whole lot of you don't really need to be super creative to do this. You just have to understand what's written and implement it. So if you look at my code, the code itself I think is longer than best investing. Yeah, just because it's a little bit more tedious what's going on. But all I'm doing here is that we're recording what the score is, what the max lead for each player is, and then the current streak and max streak for each player to see what the longest consecutive streak is. And then basically for each point, if a player was not nommed, then the score, I'm just using it to count the lead that not nommed has in particular. So if the score is bigger than not nommed's biggest lead, then replace that. Then with the streak, we'll increment not nommed's streak, current streak. If the current streak is better than the best streak, then we replace the best streak. And then because not nommed had a point, Irglak, if you had a streak, that gets cancelled out. And then this is just the exact mirror image if Irglak had the point. Then once we've gone through all of these points, we'll compare the maximum streaks to figure out who wins under the first system. So win 1, I'm just saying, is the winner not nommed or Irglak, or is it a tie? And then same thing with the maximum lead. Is the winner not nommed, Irglak, or a tie? And then if they're the same, we agree. If they're not the same, then they disagree. Yeah, any questions about this one? I consider this one of those problems that are sort of easy but tedious. Okay, if there's no questions about this, then I'll just, quickly look at test drive. So test drive, this was the easiest problem out of everything, so I'll just very quickly go over it. Well, it's easy, but you do still need to be careful with how you read it. I think there are still some interesting submissions that didn't quite read the problem properly. So in this problem, we have these three positions taken at 3 points in time, A, B, C, and the question is if these are taken at equal points in time, and they represent the position of the self-driving car, did the car brake during that period? Did it accelerate? Did it cruise the same speed? Or did it switch direction? So in this case, for example, we see 1, 2, 3 is going at the same speed. Here it's accelerating, so this is where you have to be slightly careful just because it's accelerating in the negative direction. Here it switched direction, it turned around, went from 8 to 9 to 7. And in this case, it slowed down, so it braked. So let's quickly show you my code for this one too. Yeah, this one should be relatively easy. Actually, even this code is more complicated than it needs to be, because so we're looking at S1. That's the speed in the first interval, so B minus A. S2 is the speed in the second interval, so C minus B. Because really, what we care about is not so much the positions, but the speeds, because we're talking about acceleration, deceleration, and change of direction. So first, we want to check did the direction change? So did it go from positive to negative or negative to positive? So this already is actually more complicated than it needs to be, because what we're doing here, we want to check if one is positive and the other is negative, but it could just do that by checking if the product is negative. So that's just a easier way to do the same thing. So if the product is negative, so if we're going in a different direction, then we've turned. And one issue that I saw was that people were doing this if-elif stuff, but in the wrong order. Like some people were doing turned at the end, and that gave them the wrong answer. So got to make sure you're doing your cases in the right direction. So if it's in the opposite direction, they turned. Otherwise, we only care about absolute values, because if the second speed in absolute value is bigger than the first speed, then it accelerated. Otherwise, if the second speed is smaller, then it braked. And otherwise, then the two absolute speeds are the same, and so we print cruised because we cruised at the same speed. So yeah, those were my 3 problems that I did for the contest. Any last questions? I'm not seeing any other questions in the chat. So, okay, well, thanks for watching my presentation, and I hope you have fun with other programming contests in the future.